Well, someone went to the bathroom. Well, you could have gone earlier.
I'm recording. All right, so relate exploration 1 from 9.4 to integral test. All right, so 9.4 exploration 1. Jeez. Yeah. Okay. Even though I haven't said anything, it's 40 seconds in. Okay, so one of the tests is something called the integral test. So if you meet the criteria, which I'll show you in a second, of a series, we're trying to figure out if a series converges or diverges, you can just turn it into an integral and see if the integral converges or diverges, and that's what we're kind of showing here. So if we're trying to figure out the sum of 1 over n, it's called the harmonic series. Is it going to converge or diverge? Well, they showed a little bit here in the book of why the series will diverge. So 1 over x is just this curve. So if we integrated it from 1 to infinity, do you remember if it converges or diverges? 1 over x. It diverges because p equals 1. Very good. Okay, so I have a divergent integral, and then the series is adding up all of these boxes. And you can see that each individual box is greater than the curve, and this becomes kind of like a direct comparison test. If the area of the boxes is greater than the area under the curve, and we know the area under the curve diverges, then the series must also diverge, because it's bigger than 1 over x. And then same thing for 1 over x squared, the integral of 1 over x squared. Does that converge or diverge? It converges because p is 2. If it's greater than 1, it converges. And all of these are underneath the area under the curve. And the area under the curve is a finite number because it converges. So then the series of the summation of 1 over n squared from 1 to infinity must also converge because it's less than the curve that actually converges. Now, I looked at this and I thought, well, isn't that convenient? It kind of discredits this whole proof. If you look at this, what RAM are they using here? They're using LRAM, right? And what RAM are they using down here? RRAM. If you did LRAM on the bottom, you couldn't prove anything because the area of the box is bigger than the area under the curve, so it could either diverge or converge. Likewise, if this was using RRAM up here, if I have a divergent area under the curve and something smaller than it, then we don't know anything either. So I guess they literally just use LRAM or RRAM, whatever they need to make their proof, I guess. But there is an integral test that can be used to evaluate if a series converges or diverges. If that's what you remember from everything I just talked about, then you're good. You can just change it into an integral, see if that converges or diverges, and then you know the series will converge or diverge. All right, so yeah, no matter what. Well, it has to be continuous, has to be positive, and it has to be increasing. Those are the 3 criteria for integral test. So, like example 1 of the book. This is continuous. They're all positive. And as we add terms, each one is smaller than the previous one, so it does decrease. Those are the three criteria that you need for the integral test. It does meet all three criteria, so then you just change it into the integral. And at this point, I would just say P is 3/2, so it converges. So then this converges. Just to make our life easier, you can simply say right here that P equals 3/2, it converges. You don't have to do the whole integral. So just recognize that if it's like 1 over n to the power, in this case n to the 3/2 in the bottom, you could just say converges P equals 3/2, just like we did with integrals.
Can you explain the P stuff again?
Yep, you bet. So if the integral or series, if it's 1 over n to the p, I'll do it with just the series. If p is greater than 1, it converges. And if p is less than or equal to 1, so basically between 0 and 1, including 1, it diverges. So 1 over p n to the 1/2 would diverge. 1 over square root of n diverges because it's 1/2, which is less than 1. So I told you there's a harmonic series. We just talked about the harmonic series. Harmonic series is just 1 over n as it goes to infinity. And we know if p is 1, does it converge or diverge, Lily? If p is 1.
It diverges.
It diverges, very good. So the series 1 over n to the 1 over n is going to diverge. What if it's 1 over n to the 1.000, how many zeros there are? 1. Will it converge? It will converge because it's bigger than 1. How quickly will it converge? Well,
Very, very slow.
approximately how many terms? Oh. So if I have, how many terms of the harmonic series are equal to the form of a partial sum larger than 20? Well, I guess that was a different thing. So if we know that 1 over n diverges because it goes to infinity, but how closely or how quickly does it get there? This is just kind of interesting. So this is how many terms, 178 million terms, adding them all up.
Well, it does approach 0, so.
Yeah. So it will eventually become infinity, but that's how slow it is. Like what's something really slow?
Snail.
Turtle? Snail. Yeah, snails are slower than turtles, aren't they? That's like a sleepy snail on a frigid January day, trying to. Okay, so getting into some more nuts and bolts here. Limit comparison test. Hopefully that sounds familiar. The limit comparison test is when you find one other thing to compare it to. You can't really see that very well. Okay.
Is that the n plus 1?
No, that's the ratio test.
Oh.
The limit.
I get that one.
The ratio test is pretty useful, isn't it?
Yeah.
Yeah.
Can we use that on we use that on anything?
No, not in anything. No. But it's a good thing to have in your arsenal, right?
Yes.
Okay, limit comparison test is another thing that's used often. So if we're trying to figure out if a series converges or diverges, just find the end behavior model of what you're looking at and compare the two, and if you end up getting a constant where you find the ratio of that over the other one as n goes to infinity, then you know that they behave the same. They both converge or they both diverge. Okay, and I'll show you examples of that. If you end up getting 0, well, if you compare something to something else, like if I'm trying to figure out if this is 3 plus n over n to the 3/2 plus 1. Okay, so if I was trying to figure out that, whether it converges or diverges, I can find the n behavior model. So like find the biggest degree on top over the biggest degree on the bottom, and it simplifies to be 1 over n to the 1/2. Do you see that?
Yes.
This is what you're going to compare it to. And what do I know about that series as it goes to infinity? Is this going to converge or diverge? It diverges because p is 1/2, which is less than 1. Okay? So in my head, I already know the answer to this problem. Because I'm going to compare this to this. We're going to get some number, and I'm going to show you. That means they're going to behave the same. And if they behave the same, and we know that this one diverges, then the other one must diverge also. This diverges. The only step I didn't show is comparing the two. So comparing, you do one over the other and find the limit as n goes to infinity and see what we get. I can just move that up there, and you can do so dividing by that's the same as multiplying by. It's reciprocal. So I guess I could distribute. I get n to the 3/2 plus 3 n to the 1/2 over n to the 3/2 plus 1. Okay, you could do, and we've gotten pretty good at figuring this out. I think it'll end up going to 1, comparing the coefficients. All it has to be is some number. If it was 4, if it was 10, if it's 1, then we know they behave the same through the limit comparison test. Now if it's 0, if I compare, like if I compare it to 0, then I know which of the two is more dominant, the top or the bottom one. The bottom one has to be more dominant because it goes to 0. It's like the whole smaller over bigger infinities. If it's more dominant, if that's going to go to 0, then we know that this one is faster. It gets there, is more dominant. It gets to infinity faster. Okay, so if I know that if we get 0, this is more dominant, so it's bigger. If I know that this one diverges, then this one would have to diverge. And the other way around. If we get infinity, then this is more dominant, and then we can say that, well, I want to make sure I say it right. Okay, so I have A over B, and I'm comparing them. If you get a number, when you compare the two, then they behave the same. If you get 0, then B of n, or B sub n, would be more dominant. And if we know that B sub n is more dominant, it's bigger than A sub n, and it converges, then I know A sub n must also converge. Kind of like if I have n squared here, it gets there faster than n, because it's quadratic compared to linear. If I know that this one converges, then this one would also converge. Okay, so you're going to have to think that through. If you end up getting 0, more times than not, you'll get just a number. If you end up getting infinity, it's the same kind of logic. We know that the top one is bigger, and if the bottom one diverges, then the top one would also diverge, just because it's bigger than it. Okay, so example 3 out of the book, limit comparison test. Right here, determine whether the series converges or diverges. I look at that, and I think n over n squared. I could say, or you could say n over n squared. It doesn't matter the number, the constant out front, because all that's going to do is change whatever limit you end up getting. And as long as you get a number, you're good. So I have 2n plus 1 over n plus 1 squared. It would be 2n over n squared, which is 2 over n. And if I don't want the 2 in there, I can make it 1 over n. It doesn't matter. It's easier, focus please, to probably just use 1 over n. Have to give it a pen, something to focus on. So I'm going to compare it to 1 over n. So I get 2n plus 1 over n plus 1 squared over 1 over n, as n goes to infinity. So it's 2n plus 1 times n. So I get 2n squared plus n plus 1. Okay, so they're both quadratics, which is nice. The ratio of the coefficient is just 2 over 1, so we end up getting 2. Okay, so they behave the same because we get a number other than 0. Okay, what do I know about this right here, this series? Does that converge or diverge? It diverges. That's called the harmonic series. It diverges because p is 1. So then this one would diverge. Limit comparison test. All right, another one right here. 1 over 2 to the n minus 1. What's that pretty much the same as? 1 over 2 to the n. Okay, this minus 1 is infinitesimally small in the big picture. So we could compare it to 1 over 2 to the n. So I have 1 over 2 to the n minus 1 over 1 over 2 to the n, which is 1 over 2 to the n minus 1 times 2 to the n. We could do L'Hopital's. So the derivative of the top is 2 to the n natural log of 2. Derivative of the bottom is 2 to the n natural log of 2. We end up getting 1. They're basically the same thing. Okay, so they behave the same because we got a number. So now we have to know whether this converges or diverges. Well, this is the same as 1/2 to the n. So does this converge or diverge?
It equals 2.
It does converge. How do you know it converges? What kind of a sequence is that, or a series? It's a geometric. Nice work, Claire. It's a geometric series where r is less than, it's between -1 and 1. So this is going to converge. You said it converges to 2? It might. I don't know.
So is that what the ratio test does?
Well, if I want to know what it converges to, you'd do the initial. Wait, there it is. So it'd be 1/2 over 1 minus 1/2. So it'd be 1/2 over 1/2. So it actually converges to 1.
What does the ratio test do?
Ratio test will find interval. Usually ratio test involves x's. These are just n's. The ratio test will give you the interval of convergence. Like, where does it converge? We're just figuring out if they converge or not. So you wouldn't use the ratio test here.
Okay.
All right. Let us see that. And behavior is basically, what would be a good thing to compare this one to? Just think just one term on top and one term on the bottom. The biggest.
3n over n to the third.
Good. 3n over n to the third, which simplifies to be what? Yeah, so 3 over n squared, which you could just say is 1 over n squared if we want to get rid of the 3. So I would compare that to 1 over n squared or 3 over n squared. You're going to get some number, and they're going to behave the same. So what about the series 1 over n squared? That it converges because it's bigger than 1. So then this one would also converge using the limit comparison test. There's a lot of steps that you have to show, like on a test or quiz. Like you have to tell me why what you're comparing it to, it converges. You'd say it converges because p equals 2. And you have to show me that the limit of this over what you're comparing is equal to some number. Yeah. And then you would say that this converges using the limit comparison test. But I will let you go LCT if you want. You're welcome. Yep. We are done with one page from the notes. And we have not gotten even close to testing convergence and endpoint. It's like the last thing we're going to do today, which means we're not going to get to it. I know I shouldn't have written that list on the yummy and yuckies. Wait for 10 good minutes. All right. Alternating series test. Okay, so in my notes I have, you have to figure out, is it always positive? Does it decrease? Is the limit equals 0? And that's a good way of, it's a good way of thinking. Okay, so it really only has 3 things to do for the alternate series test. This is a nice one. This one goes quick. Alternate series goes quick. Okay, so if you see something that alternates, like if it goes -1 to the end, it's alternating. Sorry, it's moving around. Here's a better way, I think. It's strictly alternating in sign, decreasing in absolute value from the start. My internet went out and I had to brush off the satellite dish. That was Alex. Strictly alternating in sign, decreasing in absolute value from the start, and the limit is equal to 0. Okay, so alternate, check. Decrease in value, and does the limit equal 0 as n goes to infinity? Okay, so kind of those are the 3 things that you're looking for. Example 4. Where's example 4? Oh, the alternating harmonic series. So the harmonic series is this. And they call it harmonic. It's not a coincidence. Do you know what harmony is in music? It's like if you've got a C, E, and a G, that makes a nice chord. They're harmonic to each other, right? So in this, if you, oh, I'm out of my league on this. If you look at all the series of numbers, I should have looked this up. There is a reason they call it harmonic series, because if you play the notes on the chords of the blues, there are.
The terms in the harmonic series
Thank you.
correspond to the notes on a vibrating string that produces multiples of the fundamental frequency. For example, 1/2 produces the harmonic twice the fundamental frequency, and 1/3 produces the frequency that is 3 times the fundamental frequency.
All right. So this dude loves it. The second harmonic note is produced when the finger is positioned halfway between the bridge and nut of the string from the string is played. That connection from calculus to music. I clearly don't understand it either, but I don't know why I even mentioned it. But you explained it very well, Lily.
Yeah, I read it out of the book.
Don't say that.
All I want to do is hit stuff and dance, so.
Good for you.
Okay, so this is the harmonic series. The alternating harmonic series would be like -1 to the n over n. So it's the same thing, it just changes sign. So it's 1 over 1, 1 over 2, 1 over 3, but alternating would be plus, minus, and so on. Okay, so let's see if this converges using the alternating series test. We see that it alternates signs, so that's a good indicator. Does it decrease in value every time? I go 1, and when it says decrease in value, we ignore the negative, positive, it's just the absolute value. Okay? So like in my notes, what's my u sub n? That's just 1 over n here. Like getting rid of the negative sign. So 1, 1/2, 1/4, 1/3, 1/4, those are all getting smaller so that they do decrease in value. And what about the limit as n goes to infinity? Is it equal to 0? So the limit of 1 over n as n goes to infinity, that is in fact equal to 0. So it checks all three. So on a quiz or a test, I would say what you need to write is it alternates, decrease in value, the limit is 0, therefore converges. Alt series test. So just ask those three questions. If it meets all three, then it converges. All right. Absolutely convergent. It is absolutely convergent. Without a doubt. Okay, so absolutely convergent means that you add up all the terms, but you just make them positive. You take the absolute value of all of them. And if they all add up, or if you add up all the positive ones and it converges, the series will converge if it's like alternating, there's some positives and negatives. So if you can prove that it converges absolutely, then you can prove that it converges.
How do you prove that it converges absolutely?
You just ignore the negative. If there's an alternating sign, you just ignore it. So in this one, if I wanted to prove, does this converge absolutely? That means it would converge like this. Does this so I made it absolutely, so I went like this. Chunk, chunk. Wait, there it is. So absolute value, I made it this. Does this converge?
No.
It doesn't. So if it did converge, then we'd say, well, then that one converges, because this converges absolutely. So we can't say that this converges using that logic.
Okay.
This would actually be considered conditionally convergent, because it converges, but it does not converge absolutely. That's called conditionally convergent, which is the next thing I was going to talk about. A series that is convergent, but not absolutely convergent. There's a lot of logic in Chapter 9 to keep straight. Okay. I'll just go through here. Alright, so we have an alternating series here. So we're going to determine whether it converges or diverges using the alternate series test. So check 1, it alternates. Check 2, does it get smaller and smaller every time?
Yes.
With every term?
Yes.
Like if you don't know that, just plug in 1, plug in 2, plug in 3, and you can just say, if it's obvious, then you just say it does go down every time. And then the limit as n goes to infinity. Again, we're not talking about this, just this. Does that go to 0?
Yes.
It does. So we know that this converges using the alternate series test. It checks all three. Does it converge? Absolutely. So if you take the absolute value of that, which means get rid of the negative sign here, does that one converge? Let's do a limit comparison test. What should I compare it to? 1 over n. And if we do the limit process and we get a number, which we would, what do we know about 1 over n? P equals 1, therefore diverges. So then this one would diverge if it's absolutely. Okay, so let me ask you a couple questions. Does this series converge?
Yes.
It does. Through what test? How do you know?
Wait.
The other A word.
Series.
Yes.
Right, so this one converges, alternating series test. Does it converge? Absolutely.
No.
No, and we just went through that because we compared it to 1 over n, and 1 over n diverges, so this one diverges. Okay, so you would call this series a conditional, it converges conditionally. Because it converges, but it doesn't converge absolutely. And that's when you know they're called conditionally convergent. All right. Oh, we're done with that page. We're picking up some steam here. Okay, I'm just going to go kind of quickly through the nth root test because it's not as important. I don't think there's only a few problems toward the end of the assignment. And then I want to close with checking the endpoints. Okay, so the nth root test, or the root test, means if you take it to the nth root, whatever you're trying to figure out the series, if you take the nth root of it and then evaluate the series as it is, well, if the series it is convergent if the limit is less than 1. If you get greater than 1, it's divergent. If you get 1, then it is inconclusive. And you're actually finding the limit as n goes to infinity. So right here, I would use the root test because there's an n on the outside as an exponent. So if I take the nth root of it, or take it to the 1 over n power, that disappears. Okay, so now the series is going to behave the same as whatever what we get as n goes to infinity. So we're going to ignore the n on the outside. So I'm trying to find it here. We're going to get rid of that and find the limit as that goes to infinity. Do you see that you're going to get 1/2?
Yes.
Okay, so 1/2 is less than 1, so it converges. If it's less than 1, it's absolutely convergent, which means it converges. If you get greater than 1, it diverges, and 1 is inconclusive.
So it's like harmonic?
In R, kind of like that. Yeah, if you want to think of the same logic, yep.
Do we have to be able to tell whether it's absolutely convergent or if it's conditionally? Is that going to be
Not for this type of problem. Yep, yep. Good question. She asked it, would they be conditionally convergent? Probably not in this type of problem. I'm going to skip the next page too. I'm going to jump to example 6, which is a really good example. I guess it's out of the book. Okay. So up until this point, we have used the ratio test to find intervals of convergence, but we have not checked the endpoints. Okay, what I mean by endpoints, if I end up getting x plus 4 less than 1, then I know that the center is at -4 with a radius of 1. Well, I'll show you. X plus 4 is less than 1, or the opposite of x plus 4 is less than 1. So x is less than negative 3. And greater than negative 5. Okay, so on our number line, if you're trying to figure out the interval of convergence, it's between negative 5 and negative 3. Right?
Yes.
That's where it converges, because the center is right at negative 4. Up until this point, we've just been good with it. Okay? This I would call the initial interval of convergence. What we're going to do now is check to see if it converges at negative 5 and if it converges at negative 3. It might converge at the endpoints also. Okay? So we go through this same thing that we have done, the ratio test, got our interval of convergence, negative 5 to 3, but then all you have to do is make x negative 5 and plug it into the original and see if it converges at that point. And then make x negative 3, plug it into the original, and see if it converges or not. Okay, so an example 6. I want to make sure I get to it. Okay, where does it converge? So we'll do the ratio test. So that's the x minus 3 to the n plus 1 over 2n plus 1 divided by that, so it's 2n over x minus 3 to the n. Remember, n is going to infinity. And the x's actually have an absolute value, but it's going to be x minus 3, and then 2n over 2n plus 2. This just goes to 1, so it disappears. So I do get x minus 3 less than 1. Okay, so my center is at 3, my radius is 1, so we're going from 2 to 4. I just skipped the whole inequality thing. Okay, so from 2 to 4 is my initial interval of convergence. So we're going to plug in at x equals 2 and at x equals 4. We're going to do like sub-problems here. So far we haven't done anything different. All we have to do is check endpoints. So at x equals 2, let's see if it converges. So you go back and plug 2 in for x, so it becomes the sum of negative 1 to the n over 2n.
It converges.
How do you know it converges?
The alternating series test.
Okay, so we're told that Lily said it converges alternating series test because it does alternate, it gets smaller, and the limit goes to 0. So you'd have to check, converges. Alt series test. So my new interval of convergence is going to include 2. Because it converges on the endpoint when x is 2. So let's plug in 4. That's going to get you 1 to the n over 2n. Well, 1 to the n is just 1. So it's just 1 over 2n. Is that going to converge or diverge? It's going to diverge. Now how do I know that?
It's just harmonic.
It behaves the same as harmonic. Very good. So we're doing a comparison test. Compare it to 1 over n. And you get a number. 1 over n diverges because p equals 1. Or you could say 1 over n diverges because it's harmonic. Okay, so this diverges.
Can you also say because of p-test?
Yep, or you could say p equal to 1. Yep. You can't say p here just because it's 2n.
Okay.
It's a little bit messy. Yeah. If you wanted to pull 1/2 out front, then it becomes a harmonic. But okay, so that diverges, so we don't include 4. So our interval of convergence is from 2 to 4, excluding 4. So that's just checking endpoints. Another subproblem within one problem. So at 2, if x is 2, does it converge? If x is, yes. So if x is 2, does it converge absolutely? So plug 2 in and make it absolute value. Does it converge at 2 absolutely?
No.
If you plug 2 in, we get this. Does this converge absolutely? It doesn't, because if you get rid of that negative, it's going to diverge. So if you were asked, where does this converge conditionally? It converges conditionally at 2, because it converges, but does not converge absolutely. That's the only place that it would be conditionally convergent, just at x equals 2. You're going to have a bunch of problems in your assignment where it'll say, find the interval of convergent. Is there anywhere where it converges conditionally? In this problem, it converges conditionally at 2. And you recognize that because it has a bracket, not a parenthesis when you're done. If you want to dumb it down, if you included it in your interval of convergence, that's usually an indicator that it's going to converge conditionally at that point.
Like that. Can I do it for line? Like the inequalities of the line?
Like this? With a line? What do you mean? Oh, like x is greater than or equal to 2?
Yes.
Yeah.
Sure. Yep. Okay, we didn't get through all their examples. This is the one that I wanted to go through, D for sure, but that's all the time we have. I'll research my harmonic influences in calculus.